Welcome to this problem-solving session. Today, we'll be diving into problem number 2193, minimum number of moves to make palindrome. This is a fascinating problem that challenges us to think critically about string manipulation and optimization. Let's explore the approaches and break it down step by step. The problem we're solving is to determine the minimum number of adjacent swaps required to turn a given string into a palindrome. A palindrome is a string that reads the same forwards and backwards. The input string, S, will consist only of lowercase English letters, and its length will be an even number ranging from 1 to 10,000. The only operation you're allowed to perform is swapping two adjacent characters in the string. Our task is to calculate the minimum number of such swaps needed to make the string a palindrome. If it's not possible to rearrange the string into a palindrome, the output should indicate that as well. Let's look at some examples to understand this better. In the first example, the input string is S equals AB. The output is 2, meaning it takes 2 swaps to turn this string into a palindrome. Here's how it works. First, swap the second A with the first B, which gives us the intermediate string ABAB. Next, swap the first B with the second A, resulting in the string ABA. This final string is a palindrome because it reads the same forwards and backwards. The minimum number of swaps required to achieve this transformation is 2. Now, consider the second example where the input is S equals LeetCode. The output here is also 2. In this case, we start by swapping the first T with the E in the middle, which gives the intermediate string LT. Then, we swap the second L with the first T, resulting in the string LeetL. This string is now a palindrome, and the total number of swaps required is 2. This example demonstrates how we can strategically rearrange the characters to achieve the goal with the minimum number of swaps. For the next input, S equals ABCD, however, things are different. For the input string S equals ABCD, the output is -1. This indicates that it's not possible to rearrange the string into a palindrome. The reason is that a valid palindrome requires characters to have a symmetric distribution, where each character appears an even number of times, except possibly one in the center. In this case, the characters in ABCD all appear exactly once, so there's no way to rearrange them into a symmetric pattern. When the required symmetry is not achievable, the output must be -1. Now, let's discuss some constraints and edge cases to further clarify the problem. Strings that consist of all identical characters, like AAA, are already palindromes. For such cases, no swaps are needed, and the output should be 0. On the other hand, longer strings with more complex distributions, such as apt, require careful analysis to determine the optimal swaps needed. It's also important to note that if the length of the string is even and any character appears an odd number of times, it's impossible to form a palindrome, and the output should be -1. These edge cases highlight the importance of understanding the frequency of characters in the string to determine if a valid palindrome is even possible, and if so, how to achieve it with the minimum effort. To tackle the problem of transforming a string into a palindrome with the minimum number of moves, we first consider the brute force approach. The intuition here is straightforward. For each character in the string, we repeatedly swap adjacent characters to bring them closer to their mirrored positions. Starting with the outermost characters, we check all possible swaps to ensure that the string gradually becomes a palindrome. However, this method is highly inefficient. The nested loops used for character checks, finding matches, and performing swaps result in a time complexity of n cubed. This makes it impractical for strings of even moderate length. The drawback lies in the sheer number of operations required, making it computationally expensive. To address this, we shift our focus to an optimized greedy approach. Here, the key idea is to directly locate and reposition matching characters, minimizing the swaps needed while ensuring the string transforms into a palindrome. This approach is more targeted, as it avoids the exhaustive testing seen in brute force by focusing only on the necessary actions to achieve the desired result. The implementation of the optimized greedy approach involves a few steps. First, we use 2 pointers, one starting from the leftmost character and the other from the rightmost. For each character at the left pointer, we locate its matching character on the right side. If the match is already in the mirrored position, no action is required. Otherwise, we move the matching character to the correct position by performing adjacent swaps. For cases where no match exists, which can only happen in strings of odd length, the unmatched character is placed in the middle. The time complexity of this approach is O(n squared). As for each character, we may need up to O(n) swaps in the worst case. The space complexity is O(1), making it memory efficient. This method is significantly faster than brute force, making it suitable for practical input sizes. We also briefly considered an alternative recursive approach, where the problem is broken down into smaller subproblems. While elegant, recursion introduces additional overhead due to repeated function calls, making it less efficient than the greedy solution. The strategy we ultimately chose is the optimized greedy approach, as it strikes a balance between simplicity and efficiency. The key insight here is that minimizing the number of swaps can be achieved by directly locating and repositioning matching characters, rather than testing all possible combinations. This approach ensures that we make the most impactful moves at each step, resulting in a solution that is both effective and computationally efficient. By reducing the time complexity from O(n cubed) in the brute force method to O(n squared), the greedy approach becomes viable even for larger inputs. While the recursive approach is theoretically valid, it comes with additional computational overhead and is less intuitive to implement for this specific problem. Overall, the greedy method is a logical choice for balancing performance and clarity. When comparing the approaches, the greedy solution stands out for its efficiency. Unlike brute force, which involves extensive computations and is prohibitively slow, the greedy approach focuses on minimizing only the necessary swaps. This makes it exponentially faster and more practical for real-world use. Compared to the recursive approach, the greedy method avoids the overhead associated with recursive calls, making it more streamlined and scalable. However, the greedy approach does require careful implementation to ensure that the swaps are minimized and the logic is correctly applied. In conclusion, the optimized greedy approach provides the best combination of simplicity, performance, and scalability, making it the most practical solution for solving this problem effectively. This problem challenges us to transform a given string into a palindrome with the minimum number of adjacent swaps between its characters. Recall that a palindrome is a string that reads the same forwards and backwards. For instance, the string Mammoth can be rearranged into Madam with only a few swaps. However, not all strings can be rearranged into palindromes, so the first step is to check if the transformation is even possible. To do this, we examine the frequency of each character in the string. For a string to be rearranged into a palindrome, at most one character can have an odd frequency if the string's length is odd. For even-length strings, all characters must appear an even number of times. Using Python's counter, we can count the frequency of each character efficiently. If more than one character has an odd count, forming a palindrome is impossible, and we immediately return -1. This initial validation ensures we don't waste time on infeasible cases. After confirming that the string can potentially form a palindrome, we use the two-pointer approach to minimize swaps. This method involves two pointers, one starting at the beginning of the string, called left, and the other at the end, called right. The goal is to match the characters at these positions as we move toward the center. If the characters at left and right already match, we simply move both pointers inward. But if they don't match, we need to find the nearest matching character for the one at the left pointer within the substring. If the match is closer to right, we perform adjacent swaps to bring it to the right position. If no match exists, such as when the left character is the middle one in an odd-length palindrome, we move it to the center. Each swap is counted, and this count is increment for every adjacent swap performed. Additionally, the algorithm naturally handles edge cases, such as strings that are already palindromes, where minimal or no swaps are needed, or strings with odd lengths, where the middle character remains stationary. The algorithm relies on two key data structures, the frequency counter and the two-pointer mechanism. The frequency counter is critical for validating whether a palindrome can be formed, and it operates in O(n) time, where n is the length of the string. The two-pointer approach, on the other hand, allows us to efficiently traverse the string from both ends, also in O(n) time. The core operations of the algorithm include character matching and swap counting. Character matching ensures that the characters at the left and right pointers are brought to their correct positions through adjacent swaps. This process reduces the problem size step by step, ensuring that the total number of swaps is minimized. Meanwhile, swap counting keeps track of the total work done, providing the final result, which is the minimum number of swaps needed to transform the string into a palindrome. These operations work together seamlessly to achieve the desired transformation in an efficient manner. The two-pointer approach is particularly efficient because it focuses on matching characters directly, avoiding unnecessary swaps. This efficiency is complemented by the frequency counter, which prevents the algorithm from attempting transformations on strings that cannot become palindromes. The algorithm also gracefully handles edge cases, such as strings that are already palindromic or those with odd lengths, where the middle character remains untouched. In terms of complexity, the worst-case time complexity is O(n squared), which occurs due to the adjacent swaps within the substring. The space complexity is O(n), primarily due to the frequency counter. To illustrate, consider the example input mammoth. The frequency counter shows that the string is valid for a palindrome, as the counts are m2, a2, d1. Using the two-pointer approach, we first match m at both ends without swaps. Then, we swap it to align positions, requiring just one swap. Finally, the middle of the string is reached, and no further action is needed. The minimum swaps required for this transformation is 1. The solution efficiently transforms a given string into a palindrome by counting the minimum number of adjacent swaps needed. The algorithm works by iteratively pairing characters from both ends of the string. First, the string is converted to a list S to make it mutable since Python strings are immutable. We also initialize moves to track the total number of swaps. 2. The algorithm runs while there are still unmatched characters in the string. It identifies the first character S, left, and attempts to find its matching pair from the end of the string by decrementing right until a match is found. 3. If left equals right, it means there is only one unmatched character left, which must be moved to the center. To do so, we remove the character from the list and increment moves by the number of moves needed to place it in the middle. If a match is found, the algorithm removes the matched pair by popping the characters at left and right indices. The number of moves is incremented by the distance the characters needed to travel to pair up. 5. This process continues until the string is transformed into a palindrome. Finally, the function returns the total number of moves. This approach ensures minimal swaps by always focusing on the closest possible matching pair, making it efficient in both time and space complexity. Here, we start implementing the solution in Java. First, we import the necessary libraries, and then we define the main method, minMoves to make palindrome, which takes a string S as input. The goal is to calculate the minimum number of moves required to transform this string into a palindrome. We begin by determining the length of the string and creating a list of characters called charList from the input string. This list allows us to manipulate the characters more easily. Next, we initialize a variable moves to 0, which will keep track of the total number of moves. The core of the algorithm involves a while loop that continues as long as there are characters to process in the list. Inside this loop, we use two pointers, left and right, to traverse the list from opposite ends. The purpose is to find a matching pair for the first character in charList. If no match is found immediately, the right pointer is decrement until a match is located. However, if the left and right pointers meet, it means there is only one unmatched character, which needs to be moved to the center. In this case, we remove the character from the list and increment the moves counter by half the size of the remaining list, as each step toward the center contributes to the total moves. Once a matching pair is found, we proceed to remove both characters from the list. This is done using the remove method for the right pointer first, followed by the left pointer. Since removing characters shifts the indices of the remaining elements, we update the moves counter by adding the distance between the original position of the right pointer and the end of the list. This accounts for the steps required to reposition the characters into their correct places for the palindrome. The loop continues until all characters have been processed, ensuring that every step contributes to reducing the string to a valid palindrome. Finally, we return the total moves count, which represents the minimum number of operations needed to achieve the transformation. This approach ensures an optimal and systematic solution to the problem of making the string a palindrome. To solve the problem of determining the minimum number of moves to make a palindrome, let's start by walking through the first example, where the input string is AB. First, we convert the string into a list, so it becomes a, b, and initialize a variable moves to 0 to track the total moves required. In the first iteration of the outer loop, we compare the characters at the two ends of the string, the leftmost character, which is A, and the rightmost character, which is B. We adjust the right pointer to find a matching A for the left pointer, eventually locating it at index 3. At this point, we remove both matching characters, effectively popping A from both ends. After this step, the updated string becomes B, B, and since the matched pair was already at the ends, no moves are added to moves, leaving it at 0. Next, in the second iteration of the outer loop, we again compare the leftmost and rightmost characters of the updated string, which are now both B. This time, the characters at left and right immediately match, so we simply remove this pair. Popping B from both ends results in an empty string. Once again, no extra moves are needed since the matched pair was already aligned, leaving the total moves at 0. With the string now fully processed and empty, the result for this example is 0. This demonstrates a scenario where the input was already structured as a palindrome, requiring no additional moves. Now let's explore the second example, where the input string is APCA. We begin by converting the string into a list, resulting in A, B, C, A, and initialize moves to 0. In the first iteration of the outer loop, the leftmost character A matches with the rightmost character A. We remove this pair by popping A from both ends, leaving the updated string as B, C. Since the matched pair was already at the ends, no moves are added to the moves variable, which remains at 0. In the second iteration of the outer loop, the leftmost character is now B, but there's no corresponding B at the rightmost position. To handle this, we decide to move B toward the center of the string. We remove B from the leftmost position, which leaves the updated string as C. The number of moves needed to transfer B to the center is calculated as half the current string length, resulting in an increment of 0 to moves. At this point, only one character remains, so we move it to the center by default. The string is now empty, and the total number of moves calculated is 2, giving us the output for this example. For the third example, the input string is racecar, which is already structured as a palindrome. We convert it into a list, resulting in R, A, C, E, C, A, R, and initialize moves to 0. In the first iteration of the outer loop, the leftmost R matches with the rightmost R. We remove both instances by popping R from the ends, leaving the updated string as A, C, E, C, A. Since the matched pair was at the ends, no moves are added to moves, which remains at 0. In the subsequent iterations, the process continues similarly. The leftmost A matches with the rightmost A, so we remove this pair and update the string to C, E, C, again requiring no moves. Then, the leftmost C matches with the rightmost C, and removing this pair reduces the string to E. Finally, the single remaining character E is moved to the center by default, resulting in an empty string. Throughout these steps, no additional moves were needed, so the total moves remains at 0. The output for this example is therefore 0, highlighting that no rearrangements were necessary for an already palindrome-structured input. To analyze the time complexity of the solution, let's break it down step by step. The outer while loop is the first component to consider. This loop continues as long as the string has more than one character, and in each iteration, we remove a pair of characters. Since the string decreases in length by at least 2 characters per iteration, the number of iterations is roughly proportional to half the length of the string, or n/2. This contributes O(n) to the time complexity. Next, we have the inner while loop, which is used to find the matching character for the first character of the string. In the worst case, this loop may need to traverse the entire remaining string for each iteration of the outer loop. The length of the string decreases by 2 in every outer loop iteration, so the total number of iterations across all executions of the inner loop will be n plus n2, plus n4, and so on. This forms an arithmetic series, which simplifies to approximately O(n squared). Therefore, the inner loop dominates the time complexity, contributing O(n squared) overall. Now, considering the pop operations, which are used to remove characters from the list, each of these operations takes O(1) time. Since we perform 2 pop operations per iteration of the outer loop, their contribution is minor compared to the O(n squared) time of the inner loop, and can be considered negligible. When we combine all these factors, we see that the overall time complexity of the solution is determined by the inner while loop, which results in O(n squared). Shifting to space complexity, the input string is first converted into a list to allow in-place modifications, which requires O(n) space. All subsequent operations, such as popping characters, are performed directly on this list, without the need for additional data structures. Thus, the space complexity is dominated by the space needed to store the input list, which is O(n). The final space complexity of the solution is therefore O(n), as the only extra space required is to store the input list. Now, let's compare this approach with a brute force method. A naive brute force solution would involve generating all possible permutations of the string and checking each one for whether it forms a palindrome. Since there are n permutations of a string of length n, the time complexity of this brute force approach would be O(n). This is astronomically higher than the O(n²) time complexity of the provided solution. The optimized solution systematically reduces the problem size by removing matched pairs or repositioning unpaired characters, achieving a significant improvement over the factorial time complexity of the brute force method. When we analyze the best, average, and worst-case scenarios, we can see how the solution performs under different conditions. In the best-case scenario, the input string is already a palindrome. This means the inner while loop finds matching characters in constant time during every iteration, and the outer loop executes approximately n/2 times. This results in a time complexity of O(n). For the average and worst-case scenarios, the input string may have a more complex arrangement, requiring the inner while loop to iterate over most of the string to find matching characters. In these cases, the time complexity becomes O(n²), as previously calculated. In conclusion, the provided solution is efficient given the problem requirements. While it is not linear, the O(n²) time complexity is a reasonable trade-off for palindrome manipulation and is far superior to the brute force approach both in terms of time and space efficiency. When solving this problem, there are a few common pitfalls to watch out for. One of the most frequent mistakes is overlooking edge cases. For example, scenarios like handling empty strings, single-character strings, or strings that are already palindromes often get ignored. This can cause runtime errors or incorrect outcomes if your solution isn't robust enough to handle these situations. Another issue is relying on an inefficient brute force approach. While it might seem straightforward, brute force solutions usually involve exponential time complexity, making them impractical for larger test cases and leading to time limit exceeded errors. Additionally, incorrect swap logic is another area where mistakes occur. If you misplace indices or attempt to swap non-adjacent characters, it violates the constraints of the problem and results in invalid solutions. Finally, neglecting to identify the problem's optimal substructure, such as minimizing swaps to achieve symmetry, can prevent you from leveraging more efficient strategies like greedy algorithms or dynamic programming, which are often key to solving this problem effectively. Another common issue is off-by-one errors, which can arise when iterating through characters, especially if you're comparing characters symmetrically from both ends. These errors can cause you to miss necessary swaps or perform unnecessary operations, both of which can compromise your solution. To tackle this problem effectively in interviews, it's important to focus on a few key principles. First, recognize patterns, particularly symmetry, as many palindrome-related problems revolve around this concept. Exploiting symmetry can help reduce the time complexity of your solution. Next, always aim for optimal thinking. Avoid brute force methods unless specifically asked, and prioritize efficient strategies like greedy algorithms or dynamic programming. Testing your code thoroughly is also critical. Ensure that you cover edge cases, including the smallest and largest possible inputs, and strings that are nearly palindromic. During interviews, clearly communicate your thought process, especially when weighing trade-offs between approaches. Lastly, consider space complexity. If multiple approaches have similar time complexity, evaluate whether one can be implemented more space efficiently, such as solving the problem in place. This problem also connects to several related LeetCode challenges, which can help you build stronger problem-solving skills. For instance, LeetCode 5, longest palindromic substring, focuses on identifying the largest palindrome within a string. Then, there's LeetCode 131, palindrome partitioning, which involves breaking a string into the minimum number of palindromic substrings. Another important problem is LeetCode 516, longest palindromic subsequence, where the goal is to find the longest subsequence that forms a palindrome. Finally, LeetCode 1216, valid palindrome 3, is a variation that asks whether a string can be converted into a palindrome with a maximum of k changes. Exploring these problems can deepen your understanding of symmetry, dynamic programming, and other techniques you can apply to palindrome-related challenges. There are several alternative approaches and trade-offs you can consider when solving this problem. The two-pointer approach is one of the most efficient strategies. By using 2 pointers to compare characters from both ends of the string and swapping as needed, you can achieve an O(n) solution. However, this method requires careful handling of edge cases, particularly adjacent swaps. A dynamic programming approach is another option. By maintaining a DP table to track the minimum swaps needed for substrings, you can systematically build a solution. While this method is easier to implement for complex variations, it comes with a higher space complexity of O(n squared). The greedy approach is also popular, as it involves making locally optimal swaps at each step to bring the string closer to a palindrome. While fast and intuitive, this approach can fail in edge cases where a globally optimal solution is needed. Finally, recursive backtracking allows you to explore all possible swap sequences. While this guarantees correctness, it's computationally expensive with a time complexity of O(n), making it impractical for larger inputs. Each method has its strengths and trade-offs, so choose the one best suited to the problem's constraints and requirements. Great job! We've successfully tackled problem number 2193 and walked through the approaches to solve it. Remember the key techniques we discussed, and apply them to similar challenges. Thanks for joining, and see you next time for more coding adventures. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!